We're back and we're talking about the general existence and uniqueness theorem. Good, so the general first order differential equation has the form y prime is equal to f of ty. And so why I'm bringing this up is that we're going to be talking about this general form, but I want to talk about the function f for just a second. Notice that this is the domain of f, ty. It's the ty plane, right? And so when you're talking about where f is continuous, where f might be differentiable even, what we're talking about is your domain is going to be two-dimensional. So some people are a little bit thrown off by the existence and uniqueness theorem, the way we're going to write it. But it's written this way because we do have a two-dimensional domain. And so when you're looking at a differential equation, be sure you're thinking about put it in this form before you do your analysis, because this form defines what your f is going to be. Good. Okay, so let me erase this picture because we'll draw another one very similar. And we'll start off, let the IVP be given by y prime equals f of ty with f of, y of t0 being y0. Okay, so therefore in the plane, dy plane, we're starting off at this point, t0, y0. Okay, now numerically, how would you solve this differential equation? We would plug this point into this differential equation. We would compute the y prime, right? That would give us a little bit of a slope. And then we would just advance the differential equation a little bit in time to a new point. Okay, and then we would just continue that. Of course, this assumes something about the slopes, right? When you do this kind of thing numerically, you're assuming that your function is well behaved in terms of the slope. In other words, you're assuming that if the function has slope 1 here, then it's not going to be like 3 million in the next time step, in the next small time step. Right? What does that mean? That means that the function doesn't change dramatically if you're not changing dramatically in your domain. So small changes in the domain mean small changes in the range. Do you know what kinds of functions have that property? Continuous functions. So therefore, what we're going to say is let R be an, now we have to be a little bit careful. I think I'm losing my power. Let me pause for a second. So let R be an open rectangle containing T naught, and it's the largest such rectangle on which f is continuous. Okay, then a solution to the IVP exists. Okay, so that's the first half of the existence and uniqueness theorem. The second half of the existence and uniqueness theorem is a little bit harder to work through, so I'm just going to write it down and then we're going to take a look at some examples. If f and, we just had f, if partial f partial y is continuous on R, so this is after you've checked the first piece, right? So we're going to assume at this point that f is continuous on R. If partial f partial y is also continuous, maybe I should say also just to emphasize that, then the solution is guaranteed to be unique, Good. All right. And so now we've answered the existence and uniqueness question. Now there is one other question that we might be asking, and that is it possible to predict the interval? Can we predict the interval on which the solution y of t exists? Notice that for the linear case we were, right? But in the nonlinear case we may not. And so just let me try an example out for you. So it's a pretty simple example. Y prime equals y squared, with y naught being equal to y of 0 being y naught. Okay, and let's solve this differential equation. First of all, f of ty is equal to y squared. Is that function continuous? Oh yes, that's a nice continuous function. It's continuous everywhere. Partial f partial y is equal to 2y. Is that continuous? Yep, it's a nice continuous function. And so there's no issues so far with the existence of uniqueness theorem. If I solve this differential equation, I just get y to the minus 2 here. dy is equal to dt. So minus 1 over y is equal to t plus c, right? And so 1 over y, so let's just solve for y then. Y of t is equal to, I guess I could say minus 1 over t plus c. Okay, solving for c, we have y of 0 equals y0, so y sub 0 equals minus 1 over 0 plus c. So c is equal to minus 1 over y0. Good. And so we can write the answer in a couple different ways. I'm going to write the answer as, I'm going to bring the negative sign down into the denominator, and I'll write it as 1 over y0 minus t. Okay, and the reason I'm writing this like this is because it's easier to see now what interval your solution exists for. And so what will the interval be for this function? Well, you have to avoid t equals 1 over y0, right? So therefore the solution is going to be, or the interval on which the solution exists is going to be from minus infinity to 1 over y sub 0. Now the question is, let's go back to this original equation up here. Was there anything here that would have informed us that the interval would be this? Could I have predicted this from the start? No, I wouldn't. This is not predictable. And so let's go back to our existence and uniqueness theorems then. What does it say here? General existence and uniqueness theorem. If R is an open rectangle containing T naught on which F is continuous, in our case we had the entire real plane, and then so a solution exists to the IFP no matter what the T naught y naught would have been. Similarly, F sub y would be continuous on all of the reals in this case, and so we had a unique solution. But the third part, could we predict the interval on which the solution exists? The answer is no. Okay, so what you have to do then is you actually have to solve the differential equation. Like we did here, we actually had to solve the differential equation to solve for the interval on which the solution exists. Okay, and again, that's not the case if you have a first order differential equation that satisfies the existence of uniqueness theorem. Okay, now before we leave this, I just wanted to go back to our first example here. Do you remember what that was? Our first example from the previous video was y prime is equal to xy prime is equal to y minus 1 with y of 0 equals y0, right? So it's instructive to see how did this fail, or what about the existence of uniqueness theorem that would have told us that this was a problem differential equation. And so you could treat this in two different ways. So let's treat it as a linear first order, and then we'll treat it as a generic first order. Generic. Okay, so linear first order, we would divide by x, and then we would have y prime minus 1 over x times y is equal to minus 1 over x. And of course you see here, right, that x equals 0 should not be in our domain. And of course, what was our initial condition? Yep. And so the existence of uniqueness theorem then would not hold here, right? Because the existence of uniqueness theorem tells us we need to avoid 0. How about the generic case? If we treat it like that, then we're looking at y prime is equal to y minus 1 over x. And this is now your function, f of xy. And again, you see that this function is not continuous at x equals 0. So again, that's our bad point. Okay, and so what does this mean in particular here? If an IVP does not satisfy the existence of uniqueness theorem, does that mean that it's not solvable? Means not solvable? No. It just means that we cannot guarantee anything. Anything may be possible. Meaning it may have a solution, it may not. If it does have a solution, it may have one, or it may have multiple. Okay, and I've gone over my usual 10 minutes, so we'll stop there, and in the next video we're just going to look at a few examples.